Hello, everyone, and welcome to the Maintenance Community webinars. I'm Joanne, and I am one of the community admins in our Maintenance Community Slack group. Thank you all for joining us today. And if you're not already a member of our Slack group, I'll go ahead and leave a link in the chat on the right side. Today we have Rafe Britton joining for a presentation on the high school approach to understanding lubricant chemistry. I know we have a ton of lubrication enthusiasts in this group, so I'm excited for this one. I'm going to go ahead and let Rafe introduce himself in a moment, but just have a few housekeeping tasks right now. The recording for today's session is going to be available in our Slack group along with the slides that you're going to see here. Feel free to share this recording with anyone that you believe would benefit from this, as well as from hearing from Rafe's expertise. Final piece of housekeeping, you'll notice cameras are off, microphones are off on your end. So what you want to do is if you want to ask any questions, you'll use the chat feature on the right side here. Rafe will be intermittently looking throughout his presentation to see if there's questions, but we'll also leave time at the end. And any questions we don't get to, Rafe and I will obviously be in the Slack group in case there are any further questions. And that's all from me. So thank you again for coming, and I'll hand it over to you, Rafe, to get us started.
Cool, thanks, Joanne. Good day, everyone. My name's Rafe. So I'm a lubrication engineer. I work out of Sydney, Australia. So probably a slightly different time zone to a lot of the people on the call. As Joanne mentioned, I'll be monitoring the chat box throughout this presentation. So if you do want to jump in at any stage, just let me know, and we can either rewind or we can go forward. We can have a discussion. Anything. I play it pretty fast and loose here. So a bit about my background. So I'm a lubrication engineer, as I mentioned. I used to work for Mobile Lubricants, currently working as a sort of a private consultant, mostly into the industrial space. So helping companies either with lubricant selection, understanding, like training, doing things like rationalization of products and things like that. So that's primarily what I do, and I think the reason why I do what I do is because there are a lot of companies out there who might have, let's say, multiple suppliers. You might have a Shell, Mobile, Fuchs, whoever on site, and I think they just get the feeling that they're being told a different message by each of the sales reps, and all they're looking for is someone who's independent who can sort of adjudicate, if you like, and so that's sort of the void that I fill. What I'm going to be presenting on today is something that's a little bit close to my heart, which is the high school approach to lubrication chemistry. So one of the things that I have tried my best to emphasize is the fact that lubricants are just not very well understood, and I think in many ways that is the fault of a lot of the oil companies who haven't really done an adequate job of explaining how it is that they function. Now, part of that is there's a commercial role in that, right? Which I get, which is that the oil companies, they have trade secrets and they don't necessarily want to reveal everything about how their lubricant functions because some of it's proprietary technology. But at the same time, I think we can put a basic framework around our understanding of lubricants and lubricant technology. And for a lot of you guys who might be end users of these products, it's really going to arm you with a lot of information that you can then take to your suppliers to ask maybe better questions. So that's what I'm trying to achieve here. So I'm going to go through a lot of really fundamental concepts in lubricants. But everything that I run through here, you would have learnt in, like, let's say grade 10 or grade 11 chemistry. There's really nothing kind of beyond that. It's more putting a framework around how lubricants work. So I'll really get started, and ultimately what everything boils down to in the world of lubrication is intermolecular forces. So when people describe different types of additive chemistries and different types of base oils, if you understand the fundamental forces that are at play, you're going to be able to understand a lot of the different phenomena that we come up against with lubricants. And intermolecular forces are all about bonds and bonding. And within the chemistry world, there are only a number of bonds that we need to learn about. We can generally split the intermolecular forces into nonpolar and polar bonds. So what is something like a nonpolar bond would be most let's say mineral oils exhibit non-polar behavior. Something like polar would be something like water or a polyalkylene glycol. Now, polar bonds can kind of be split a little bit further into both hydrogen bonds and standard polar bonds, and we'll get into exactly what that means. But a lot of the interaction of a base oil or of an additive really comes down to the strength of the bond, and it helps us to be able to rank the different types of bonds by their strength. And to understand it a little bit, what we need to understand is that at an atomic level, all bonds are electrical. There's only a handful of fundamental forces in nature, right? There's the strong nuclear force, the weak nuclear force, and then you've got, the electric or coulombic forces, and that's really what's at play. Obviously, the fourth one is gravitational, but that's for very, very large objects. So bond strength is determined by the electrical interaction of different atoms. So if we can understand that electrical interaction, we can understand a lot about how lubricants function. So going back to our very, very basic model of how an atom looks, I'm going to pick helium just because it's easy. So you've got neutrons, you've got protons in the center, and in our common model, we understand that there are electrons which sort of rotate around the nucleus. Now, for practical purposes, that's not strictly speaking correct. The electrons are more like I think they're known now as a probability density field. So you can imagine them kind of like a cloud that moves around the nucleus in some kind of random pattern, right? So let's have that picture in our heads as we start to talk about these molecules. Now, with the electrical interactions, right, we can rank them. So there's ion-ion forces, ion-dipole, hydrogen bonds, dipole-dipole bonds, and then London dispersion forces. And so let's go through what each of those are and what that means for lubricant chemistry. So on the first one, for ion-ion, really what that means is the bonding between a metal and a non-metal. On the periodic table, that means basically taking something on the bottom left and reacting it with something on the top right, right? So, one of the most well-known ones would be take sodium and chlorine, you react them together and you get sodium chloride, right? I think that's, table salt. Everyone's pretty familiar with that one. Now, the strength of the ion-ion bond, it can be described here, where it's some constant K, the charge of the two particles represented by Q1 and Q2, and the radius squared, right? Now, one thing that you'll notice is that some ions are charged more than others. So as an example, if I switch this out for magnesium oxide, right, they have double the charge of sodium chloride, right? Because it's magnesium 2 plus and oxygen 2 minus. Right? So that can increase the strength of the bond. The other thing that can help increase or decrease the strength of the bond is the actual relative size of the molecules, right? So that R squared term is dependent on the radius of the actual atom itself. So ion-ion, materials tend to arrange themselves in sort of a crystalline structure when they're solid materials. So a classic example would be table salt. All right, so that's ion-ion forces. And let's move on to the family of polar bonds, right? So iron dipole, hydrogen, and dipole dipole. So that first question we've got to ask ourselves is, what is a dipole? When I say that, what do I actually mean, right? Now, what I'm showing here is a molecule of polyalkylene glycol. So that's a base oil that you may have seen in, let's say, compressor type applications, in some worm gear drives as well. You'll see polyalkylene glycols. And this is what the structure of the molecule looks like. Now, the key to this is understanding how certain atoms like to hold on to electrons, right? And that's called electronegativity. So let's say, for example, the bond between an oxygen and a carbon, what that really represents is the oxygen and the carbon sharing a pair of electrons. But when we go over to the periodic table, there are these numbers called electronegativity values. So carbon has an electronegativity value of 2.55, oxygen has 3.44. And in broad terms, what we say is if the difference is more than half, then that bond is polar, right? So for our practical purposes, and then hydrogen's 2.2. For our practical purposes in this oxygen to carbon environment, the oxygen actually likes to hold on to the electrons more than the carbon does, right? But between carbon and hydrogen, the electrons are approximately shared equally because they had very similar electronegativity values. Right? So what does that mean for an actual dipole? So because the oxygen likes to hold on to those negatively charged electrons more, what that means is that there is a net charge across that molecule. So the oxygen is like that area of the molecule is more negatively charged than the carbon is. And that's what we would call a dipole, which is indicative of the polarity of the molecule, right? So if we have an area of the molecule which is more highly charged than the other, what that means is that when I stack these molecules on top of each other, because now the carbon area is positively charged and the oxygen area is negatively charged, negatives and positives attract each other, right? So now the oxygen side is going to be attracted to the carbon side. And that makes the bonding of a polyalkylene glycol quite strong, right? So it tends to bond with itself. And that's why polyalkylene glycols have characteristics like really high film strength. The other thing that does is that it does mean that it can also bond with other charged molecules. So if I just had a sodium ion, for example, it's positively charged and the oxygen in the PAG is negatively charged, so they are going to want to bond together as well. And that's why polyalkylene glycols have very high, what we would call solubility, right? So we'll get into this later, but when molecules of base oil oxidize, they produce polar compounds. They produce charged compounds. And so in a polyalkylene glycol, it will be able to absorb more of those degradation products because it is itself a charged particle. Whereas in a non-polar molecule like a polyalpha olefin, then those deposits just drop out of solution because they have nothing to attach to. It also means that a polyalkylene glycol, you might have be aware that they like to take on water. They're what we call hygroscopic, right? So they take on water either from moisture or if there's contamination, they tend to hold on to water a lot. And that's because water is itself a charged molecule, right? So we have oxygens and hydrogens. So the hydrogens in water are net positively charged. And so they like to bond with the oxygens in a polyalkylene glycol. And that's why PAGs tend to hold on to water much more so than other lubricants do. All right, so let's move on. Now that we've talked about that, let's talk about the last class of these molecular bonds, which is called London dispersion, which are far and away the weakest. So London dispersion forces, if you can imagine, here I'm showing just a straight chain hydrocarbon, so it has no polarity to it. All those electrons are really, we can represent them as sort of clouds of electrons. And I'm only going to put 6 in here for simplicity's sake. But they kind of move about in random motions. Now, if I were to kind of freeze them in place, so if I were to take a photo of this molecule and have a snapshot in time, purely by random chance, at some points in time, more of the electrons are going to be on one side of the molecule than on the other side, purely by chance, right? So that's going to happen every now and then. But what that means is that there is a net dipole at that instant across the molecule, right? So one is slightly more positively charged and the other is more negatively charged. And so if we were to bring another like-for-like molecule, what's going to happen is it's going to have what we call an induced dipole, where the negative charges are attracted to the positive end of the adjoining molecule, and it induces a dipole in it. So that's how they tend to interact. So it's more of a, let's say, a surface area interaction. And so with non-polar molecules, the strength of the bond is really dictated by the surface area of the molecule. And so by understanding the shape of the molecule, you can get a better handle on how it bonds with itself. All right. So the big takeaway from this is that all bonds at a molecular level are electric in their nature. And as we go down the list, the bonds get weaker, right? So actually, I really should have that arrow the other way around, right? Bond strength goes up as you go up the list. Now having built that framework for ourselves about understanding the different kinds of forces, we can now start to explain different physical characteristics of these lubricants. So as an example, let's just talk about miscibility. Now, miscibility is a really important property to understand because it governs, for example, how water behaves with your lubricant. So is water miscible in your lubricant? It also helps govern things like flushing procedures, right? So if you want to switch from one lubricant to another and they are incompatible, that's usually because those products are not miscible together. So if I want to say, for example, go from a synthetic polyalpha olefin to a synthetic polyalkylene glycol, I can't flush one with the other because they're not miscible. So generally, I'll have to take an intermediate step where I flush the PAO with an ester because those two are miscible, and then I can then flush with a polyalkylene glycol because that is also miscible with the ester. So the ester sort of sits in between the two of them. All right. Now, most people's interaction with miscibility, and the thing that we'll probably have learnt in high school, is this idea that oil and water don't mix. So they're immiscible liquids. Right? So what does that really mean? Okay, so if I take a little jar of water and I pour some lubricant into it, generally what happens is that you get bubbles that coalesce, and generally because water is more dense than the lubricant, it sort of falls to the bottom and you get a layer of oil above a layer of water. And we've all seen this happen where we've poured oil into water. You've probably done that experiment a million times, either with your kids or in high school. And what you get is separation of the two, right? And so when we say that oil and water cannot mix, what we are in some ways talking about is the fact that like dissolves like. You've probably heard that term. And water and oils are not like each other. Right? And so that goes down to this concept of miscibility. Now, the miscibility of lubricants with each other is even more complicated than that, because we have miscibility of the base oils, miscibility of the additives, solubility of contaminants, right? All of these things are sort of playing together. But if we understand the miscibility rules, then it can help us understand what happens to additives and contaminants when they start to form in an oil. So when we are talking about mixing oil and water, what we are talking about is a solute and a solvent. Right? Because these are both liquids, we call it miscibility. Had one of these been a solid, we would have just called it solubility. And what's happening in this instance is that we have water and oil. Water forms hydrogen bonds, but oil, if it's a straight chain paraffin, can only form London dispersion forces, right? So there's a mismatch between the bonding of these two different molecules. So if I try to mix them all together, right, I mix them as hard as I can, what's going to happen is that the straight chain paraffin has no charge, right? It doesn't really have any capacity to interact with anything. But the waters, on the other hand, are all of them. They're all charged. So what happens is that over time, right, these charges are going to attract each other, and eventually the water coalesces. So in this instance, oil is completely passive. It actually is not doing anything. But all the water is attracted to each other. And so it's the water which is actually coalescing together. And as a result, hi Amir, yes, the presentation has started. I'm about 25 minutes in. I'll keep going. Okay, so it's the water which is coalescing together versus the oil. All right. So, so that's what we're really talking about, and that helps us understand which liquids are miscible with each other, right? So again, based on this ranking, right, we can talk about the different kinds of lubricants. Oh, sorry, Amir. Maybe just a quick check. Can everyone else see the presentation? Okay. So Amir, if you can't see it, then maybe we'll have to make sure that we send you the link for the rest of the presentation. All right. Okay, so let's go through the miscibility of the different liquids. So as we go from water to a polyalkylene glycol to an ester or an alkylated naphthalene, and then you've got mineral oils and polyalpha olefins, the amount of polarity in the molecules decreases as we go down the list. So water can form hydrogen bonds. It's a very polar molecule, and PAOs are almost completely non-polar. So that helps us develop some miscibility rules based on what the actual molecule looks like, right? So as an example, a PAO and a PAG are not miscible with each other because the types of bonds that they form are too different, right? So that helps us predict that behavior. Whereas a polyalkylene glycol, or say let's say a PAO and an ester, they are similar enough with each other that they are miscible, right? And similarly, an ester is miscible with a polyalkylene glycol. And generally, if you wanted to understand kind of the polarity of different molecules, we actually have a test that's called the aniline point. Right? Esters sit on one end, the mineral oils sit on one other end, and alkylated naphthalene sort of fit in the middle. Polyalkylene glycols would be way to the left. Now, what they do in this test is that they take a molecule that's called aniline, and it's quite polar, so it has a kind of a benzene ring attached to a CH2 group, and you basically try and mix the two substances together, so aniline and an ester, or aniline and a mineral oil, and you mix them together, and you see at what temperature do they remain miscible, right? And so the lower the temperature that you can go with them continuing to be miscible, is the kind of the lower the aniline point. And so by comparing the aniline points, it can help predict that behavior. So now let's go on to another physical phenomena, which is related to miscibility, but is very common in things like, let's say, for example, steam turbines. And let's talk about the demulsibility of a lubricant, because that's a really important property for a lot of people. So again, we're operating under this principle of oil and water cannot mix. And so the idea is, right, that you take the demulsibility test is one in which you take a volume of oil, you take a volume of water, you mix them together, and then you allow it to stand for a certain amount of time, right? So then once they're mixed together into an emulsion, we would call it, then we start the timer. And what we're trying to see with demulsibility, so an oil with good demulsibility is one which will break the emulsion faster. So we're looking for water and oil to separate really quickly, right? So what happens is you start the timer, it starts to go, and slowly these two liquids are going to separate out from each other. Now, generally, remember, the specific gravity of water is higher than the specific gravity of the lubricant, so it's generally going to sit on the bottom. There is a couple of exceptions to that rule. So a polyalkylene glycol, for example, has a specific gravity which is higher than that of water. So PAGs tend to go to the bottom of a reservoir, and the water will actually sit on top. But that's generally an exception. Right. Let's say it took 33 minutes for this particular mixture to completely separate. So what we would generally do is we would give you a number which is 40, so that's 40 mils of oil, right, with 40 mils of water, and 0 of the emulsion remaining after 33 minutes, right? That's how we kind of describe that demulsibility test. However, if we went back and after, let's say, 30 minutes, there was still some emulsion remaining at the top, right? We would describe that as a 39-39-2, after 30 minutes. All right. Now, emulsions for some people seem like relatively complex substances, and predicting the behavior of an emulsion can be a little bit difficult. But the reality is that we've seen lots of emulsions in our day-to-day life. So butter, for example, is actually a water in oil emulsion, right? Milk is an oil in water emulsion. So they're sort of flipped upside down. And one of the best ways to demonstrate emulsions is actually mayonnaise, right? So mayonnaise is an emulsion of oil and water. And of course, it's a very, very thick emulsion. And the way that we make mayonnaise gives us a bit of a clue into what governs emulsion stability. So if you've ever made mayonnaise, it's eggs, right? And some oil, and usually it's like vinegar or water or something like that. And you beat them together really, really fast. And that's what helps stabilize the oil-water emulsion. So what is it about an egg which causes the emulsion to stabilize? Well, it's actually a specific molecule in the egg, which is cholesterol, right? So cholesterol helps stabilize the emulsion. And when you look at the structure of a cholesterol molecule, it can help us understand a lot of different lubricant chemistry. So in a cholesterol molecule, that red atom is an oxygen atom, which makes one end of the molecule very polar. The rest of the molecule, right, is sort of a long chain hydrocarbon, and that end is completely non-polar. So what's going to happen is that we have a head of the molecule, which is polar and likes to be attracted to water, but we have a tail of the molecule which is non-polar and would prefer to be in oil, right? And so it helps to bridge the gap between those two molecules. So if I had a droplet of water, generally what happens is that the head wants to stick in the water, the tail wants to stick in the oil. And if I have enough of these, it can help suspend that water droplet in the oil, right? And it prevents the water from interacting with other water molecules. Now, if I were to take away the cholesterol, right, which is the emulsion stabilizer. So cholesterol is known as an emulsifier. There are many emulsifiers in sort of cooking. If you take away the cholesterol, what's going to want to happen? Remember, all the water particles are charged, and therefore they are attracted to each other. So what they're going to want to do is coalesce into a larger bit of water, which of course is going to fall to the bottom. Eventually, all of the water falls to the bottom of your sump, and at that point, you can then drain the water out. So in a lot of instances, what we desire, right, is an oil that breaks its emulsion extremely fast so that, right, it will all drop out to the bottom. Now, what's the kind of the problem with emulsions, right? The problem with emulsions is that if I took water and I have a vegetable oil and I mix them together, you would expect, right, that the viscosity of the product is an average of the two. But what we generally find with emulsions, right, of course we know this with mayonnaise, mayonnaise is a way higher viscosity than vegetable oil or water, right? 6,000 centistokes compared to, water, which is close to zero, and vegetable oil, which is about 40 at the same temperature. So there is a huge disparity in viscosity, and that's why we don't like emulsions generally in the lubricating world, because they get much thicker. The other reason that we like emulsions to break is so that we can separate out the water, right? So that it goes into an oil reservoir and the water separates out. Now, where is this going to be really important? Well, it's obviously going to be really important in places where we see the potential for a lot of water contamination. And you'll see this in the difference between a steam turbine oil and a gas turbine oil. Because with a steam turbine, we expect to encounter water, right? We expect that, no seal is perfect. So eventually some water is going to get into the lube oil system, And therefore, the demulsibility of a steam turbine oil is a critical criteria. Like, we need to be watching the demulsibility all the time. With a gas turbine, they don't expect to encounter very much water. There'll be some humidity that gets pulled from the atmosphere, but a lot of that can be vented off at high temperature and the use of desiccant breathers and things like that. So the formulation of a gas turbine oil is done in a way that it does not expect water to contaminate the oil system. And so you'll see that, right? One needs really good water separation. The other one doesn't expect to encounter water. And what does that mean? Well, if you think back to the cholesterol molecule, it had a polar head and a non-polar tail, and it attaches itself to water. That is the exact same function that detergents have, right? So the way that a detergent functions, if you think that I'm washing my hands, in the kitchen, or sorry, let's say washing a plate. With a plate, the bulk liquid is water, and I want a molecule that is going to attach itself to the grease on the plate and help that be washed away, right? So it needs to be water soluble, but attach itself to grease. So lubricating detergents operate exactly the same, but in reverse. So the bulk volume is oil, but we want a detergent which it can then attach itself to polar compounds, because contaminants tend to be polar. Right? Now, because of the way that the molecule looks, right, we need fewer detergents in a steam turbine oil because we want the water to separate out, and those detergents are going to want to attach themselves to water. So there are more detergents in a gas turbine because we also want to control varnish, which is more of a problem in those higher temperature gas turbines than it is in a steam turbine. Right? So that can help you kind of understand some of the chemistry behind it. Now, one of the other things that's really important, and the reason I wanted to sort of emphasize this, is because you might be tearing your hair out because you have a specific problem on site, and maybe your oil supplier comes and says, I have a genius solution for you. I can fix your problem. And you're praying to him, basically, like, how? And he comes up with this whiz-bang new chemistry. This kind of explanation is going to give you the tools to be able to accept or reject his offer on the basis of science, rather than him just sort of like hand waving about, performance specs and things like that. We can ask, okay, as an example, if I have a varnish problem in a steam turbine oil, and he comes with a solution which is just to pour in a bit more detergent additive, you can say no, because I know that's going to harm the demulsibility characteristics of my lubricant. All right. Now let's move on to a related but slightly different phenomena, which probably affects everyone as well, which is foam and air entrainment, right? So this has all got to do with molecular bonding as well. So there are three general types of air that we'll see in lubricants, right? So the first is dissolved air, which you just won't see. So typically anywhere between, depending on the temperature, 7 and 10% of the volume of a lubricant is actually dissolved air. Dissolved air is generally not a problem unless it breaks out of solution, in which case it becomes entrained air. And when entrained air travels to the top, right, it generally forms foam. Now, we actually want foam, right? So a lot of people think of foam as a bad thing, but the only way to get entrained air out of your system is for it to rise to the top of your reservoir, form foam bubbles, which then break, right? So we want something that forms a foam, but we don't want to form what we call stable foam, right? So foaming is okay so long as the foam bubbles break, right? And the way that they obviously break, is that they rise to the surface. And this is where people advertising, let's say, certain additives, which are silicon-based, it can be harmful. Basic explanation is that they can actually hold on to the air bubbles and keep them in solution. And air entrainment is a much bigger problem than foam is. All right. Now, what kind of characteristics govern? Good question from Ravi. What are the advantages of anti-foam agents then? So what anti-foam agents do is that generally, because they're silicon-based, silicon compounds in general have very, very low, and we're just about to get to this, they have very low surface tension characteristics. So what they do is that they attach themselves to the edge of the bubble and they lower the surface tension to the point where it actually breaks. But having too many anti-foam additives can be a problem, and I'll explain that. So again, let's explain surface tension by means of the types of bonds. So basically, the surface tension is related to the bond strength, right? So water, for example, if you've ever tried to blow bubbles with just water, nothing happens, right? the bubbles immediately break, and that's because there's too much surface tension. So the bubble is, if you like, brittle, right? So it's brittle and it breaks really easily. If you just try to do it with oil, there's too little surface tension, and this is why PAOs are extremely good at resisting foam formation, right? So, and Mohammed, changing the surface tension of the liquid, we'll get into that. So where you have stable foam is where you have, let me go back for a second. So mineral oil, because it has a little bit more polarity than a PAO, has slightly more stable foam, right? But not completely stable. And where we run into problems is if we have contaminants, right? So one of the contaminants that is notorious for this is if we get contamination with a grease soap, because grease soaps are highly polar, and as they get mixed in with a mineral oil, that will increase the surface tension of a mineral oil, and it will make the foam more stable, right? So then it won't want to break because it has just that right amount of surface tension that it's not going to want to break, right? And so that's the problem with a lot of contamination with grease. Similarly, as a mineral oil ages, a lot of the byproducts of oxidation are themselves polar, and so that helps add to the surface tension. And so generally, as an oil ages, not only is it consuming the anti-foam additives, but it's also getting more polar. So what anti-foam additives do is they reduce the surface tension, because silicon compounds have very, very low surface tension, and it helps reduce it to the point when an air bubble gets to the very top of the reservoir, it's going to break very quickly, right? So that's the whole point with foam formation. And so when we measure foam stability, we call this like foam stability. In general, you're going to have a certain amount of dissolved air, and when you shake up the bottle, it's going to form a small head of foam. And what we do is we wait to see how long it breaks. And generally, you'll get sort of three numbers. One is the foam volume after they blow a certain amount of air through, and that's known as the foaming tendency. So that in itself is not, is not necessarily bad. Foam stability is the one that we really want to concentrate on, because that's the amount of foam volume after 10 minutes. So you want that to go to zero almost as quickly as possible. And then, the third number is going to be the actual time for the foam to completely dissipate. All right. Maybe the last thing I'll get into, because I think we've got time, is to talk a little bit about microdieseling, right? So now that we can understand air entrainment and how air gets into a lubricant, as well as how air escapes from a lubricant, we can help explain the microdieseling phenomenon. Because microdieseling generally doesn't happen if you only have dissolved air in the system, right? So, like I said before, the amount of air that's dissolved in the lubricant is very highly dependent on the temperature, but it's also dependent on the pressure, specifically the vapor pressure, right? So if I increase the pressure, I can actually put more of any real gas, but generally air. I can get more air to dissolve in the lubricant. So we see this very often with carbonated beverages, right? So when a bottle of Coke or something is closed, we have an equilibrium. It's a dynamic equilibrium between the headspace and between the gases that are actually in the lubricant. And for most carbonated beverages, then it's operating at about 3 atmospheres. And when we open the lid, what we are doing is that we are reducing the pressure of the headspace back down to 1 atmosphere, because it's atmospheric pressure, and that then equalizes. Oh, Amir wants to explain the difference between dissolved air and entrained air. Good question. So dissolved air, you can't see, right? It's dissolved in solution. So it's almost like salt and water. When they're soluble with each other, you can't see the salt. So dissolved air, you can't see it. Entrained air is in the bulk lubricant, but they're actual air pockets, right? So they're not dissolved within the actual liquid. Right? So that's the difference between dissolved air and entrained air. So what does this mean for us in terms of gas solubility? Well, if I take here we go. So if I take a hydraulic system as an example, this is where microdieseling probably is the most common, right? Microdieseling tends to happen when we have very low pressure, because low pressure is going to reduce the solubility of the gas in the liquid. And therefore, if I reduce the pressure significantly, it's going to cause dissolved air to break out into entrained air. So where can that happen? So low pressure, generally where we see microdieseling is at a hydraulic pump, right? Because that's where a low pressure system is becoming a high pressure system, right? Because obviously the pump is compressing the air. Generally, most hydraulic systems are designed for this. This is why we don't see microdieseling all the time. When microdieseling can occur, though, is where we have a system pressure which is lower than the design pressure. And where that happens is generally if you have like a restriction on the suction side. So maybe there's a restriction in the strainer, maybe there's a restriction in the breather to the reservoir. Somehow, right, what happens is that the lubricant goes to slight negative pressure, right? So a little bit under atmospheric pressure. And let's say the oil reservoirs are operating at about 60 degrees Celsius or something, that will cause the dissolved air to break out of solution. So now I have air pockets in my lubricant. Now, as that travels up to the pump, it's still just under atmospheric pressure. And then when it goes through the pump, it gets compressed, right? Because the hydraulic pump is exerting, mechanical work on the system, which is going to compress the air bubble. And usually it compresses from in the ballpark of 1 atmosphere to about 170 atmospheres. And it undergoes that compression really, really fast. Right. So now again, using our, high school physics, we can help explain why microdieseling occurs. Because if you've ever looked at one of these, pressure volume graphs, we have isotherms and we have adiabats, right? So isotherms are lines of constant temperature. Adiabats are, lines of constant work. And what we would say is, as the air pocket travels through the pump, it undergoes adiabatic compression. The reason we can say that it's adiabatic is because it happens basically so fast, right, that there's no opportunity for any energy to escape the system. So it's a closed system, and we are just doing work on the air. So what we know from that, of course, is that you can see on the orange arrow on the right that we've jumped between two different isotherms. So as I increase the pressure and decrease the volume, that's going to increase the temperature of the air. And once I get to a temperature of 1,000 degrees Celsius, that's hot enough to auto-ignite the lubricant which is around that air pocket, right? So I'm going to get some kind of ignition event, and that's going to lead to excessive oxidation, oil darkening. We'll get particulates in the oil system. It'll increase our oil temperature as well. So if you've got lots of air pockets that are at 1,000 degrees, that eventually has to equalize out with the rest of the lube oil system, right? So the rest of the lube oil system might be at 60 degrees, but if I have lots of air pockets at 1,000 degrees, that's going to raise the temperature of the overall system. And that can cause thermal degradation as well, right? Where thermal degradation is different from oxidative because it tends to thermally crack molecules and make them lighter. And then finally, we get surface damage. So if these explosions happen on the surface of the pump, then that can cause some real damage. So anyway, that's kind of everything that I had prepared. I mean, we're right to about kind of 1:45, and so I guess I wanted to open the floor to questions. If anyone has any questions about anything that I've explained here, I know I went through it pretty fast, but I wanted to cover as much material as possible. So does anyone have any specific questions that they wanted to put in the chat? Amir is typing. Oh, I don't know who's going to get there first. How can we detect that we have a microdieseling issue? Great question. Great question. All right, so the first thing would be an audible noise. So now, microdieseling sounds like there are marbles in your hydraulic pump, right? It's like someone dropped marbles in there, so you hear like a clattering sound. Now, the only thing about that is that microdieseling and cavitation sound almost identical. So then you're going to have to narrow down the root cause, right? As to whether, so cavitation is a, if you like, high pressure phenomenon, whereas microdieseling is a low pressure phenomenon. So you'd have to look at your system in a little bit more detail to figure out whether it's cavitation or microdieseling. Right, that's sort of my general recommendation there. You'll also see the effects of microdieseling. So if you see accelerated oxidation and oil darkening and specific particulates, then that will point towards it. Now, just as a record, so I should say, most of you on here will be familiar with Sanya Mathura. So she's a bit of a specialist in lubricant degradation mechanisms. So on my YouTube channel, which is called Lubrication Explained, the video that's going up tonight, Australia time, is actually on lubricant. I'm interviewing Sanya, and she describes the microdieseling phenomenon and the way that the degradation mechanisms actually look different to standard oxidation. So that might be one that's worth listening to for you. All right, Ahmed asks, how can you balance the anti-foam agent with the air entrained in the system? That's a really good question. So my general advice to most practitioners is don't mess with the anti-foam additives. There are two basic types of anti-foam additives. There are silicon-based ones, and there are polymethacrylates. The silicon-based ones are the most common, and the reason that you don't want to add anti-foam agents is because this goes back to the manufacturing process. When we manufacture lubricants, it's not simply a matter of taking a base oil and an additive package and then just pouring one in the other, right? That's not really how it works. So anti-foam agents, especially the silicon-based ones, are they're completely insoluble in oil. So the only way that you can get them to solubilize is that they have to have a carrier fluid around them. So the way that an anti-foam agent is introduced into the oil during the manufacturing process, they actually have an anti-foam, like an individual molecular additive, and they grow bubbles of the carrier fluid around it, and that then helps suspend it at a very specific mixing rate. Now, it is virtually impossible to replicate that manufacturing process in the field. So if anyone comes to you with a drop-in anti-foam top-up additive, I would urge you not to do it because it's going to go. It will go wrong. So how can we then counter air entrainment in the system? Where possible, if you're using a mineral oil, you want to try and pull as many contaminants out of the system as possible. So it really goes down to having good filtration, and if you have oxidative products, then you need to try and remove the polar compounds, which are generally like an organic acid, right? And there are some systems that can do that. They tend to be expensive, so sometimes the cheaper alternative is just to replace the oil. All right, Mohammed asks, can you explain more about the effects of surface tension on the liquid viscosity? That's a good question. So I wouldn't necessarily say that surface tension has an effect on liquid viscosity, but the two are related, right? So, yeah, they're definitely related. So, surface tension is generally a byproduct of the strength of the bonds between each other. And so, at the surface, right? Water, for example, has very high surface tension because it has lots of charged molecules that want to bond to each other and stick together rather than sticking to the air. So that's why it has high surface tension. Now, how is it related to the viscosity? It's sort of not, because viscosity tends to be more related to the size, the physical size of a molecule, right? So water, for example, water is always water. So it's always basically at the same viscosity. Water doesn't really get thick or thin. Whereas with lubricants, we can make longer and longer molecules. And as we make larger molecules, right, the physical interaction between the molecules gets bigger, and therefore they bond together more tightly, and therefore that increases the viscosity. Ahmed says, Sanya is great. I completely agree. Amir asks, can we explain the first part of the microdieseling phenomena again? Yeah, sure. So if I go back to the first part. So with microdieseling, okay, generally it happens at the pump, because remember, what we need for microdieseling is two things. We need entrained air, and we need a system that takes air from low pressure to really high pressure, right? So generally, in an oil system, if you have good control over your oil system, there's going to be very little entrained air in there. So, assuming you have sufficient residence time in your reservoir and things like that. But where it can be a problem is if you have restrictions in your inlet line to the hydraulic pump, because that can reduce the dynamic pressure. So what happens is, if you reduce the pressure of the oil system, that can cause air to break out, because you're reducing the solubility of the system, right? So now that air has broken out and we have air pockets in our system, when they travel up to the hydraulic pump and they get compressed by the pump, right? So they go to a much higher pressure. What that is going to do is, we know that if we compress air very, very fast, that's going to raise the temperature of that air pocket, right? So it's going to, as we compress it really fast, no energy can escape, and therefore it goes to about 1,000 degrees, and therefore auto ignites the lubricant around the air pocket. So that's how that happens. Ravi says, reconfiguring the oil feed circuit removed my foaming problem, allowing less chance of air ingress. Yes, exactly. So if you can introduce less air into the system in the first place, then your anti-foam agents won't need to work as hard, right? And you won't consume them as fast. So that's a great point. So Mohammed asks one question out of the subject: how did you prepare the graphics and the animation for today's presentation? I get this question all the time. So all of these animations are built in PowerPoint. So on my YouTube channel, which Joan has kindly linked in the chat box, my entire YouTube channel is actually built on PowerPoint animations. So when I went out on myself as a private contractor, I wanted to make sure I was spending as little money as possible, because now I'm paying my own wage, and that meant that I didn't want to buy any additional software like Adobe After Effects or anything like that. So everything that I do is actually in PowerPoint. Fortunately, I have a large enough library of these presentations now that I can kind of draw on different animations that I've already built at some point in the past. But PowerPoint has actually got some pretty powerful animation features if you know how to use them. Amir asks, am I going to upload today's presentation to YouTube? I can. Obviously, Joan is going to make it available, I think, after this on the Slack channel, right? So if anyone wants it, it'll be there. You can watch it afterwards. I probably will, because now that I have the presentation, I'll probably do a version of this and upload it to the YouTube channel as well. All right, Amir looks like he's got one last question. Oh.
Let's see if Ravi has anything left to ask. Yeah. Oh, Well, I think, yeah, these are just all thank yous, Ray. So thank you for the great presentation. Of course, I'm going to go ahead and end it here. It seems like we don't have any more questions. But as everyone knows, Rafe and I are in the Slack group. The recording will be provided there along with the slides. So if you're not a member, feel free to join us. I think I left a link in the chat. But I did want to thank Ray for being here and hosting this very valuable kind of beginner guide to lubrication. And obviously, Rafe has a ton of resources on his YouTube channel, so please feel free to check those out. I think those are some really valuable stuff on there. And so we're going to go ahead and close it out. Thank you again, Rafe, for being here. Any last words?
No, just thanks to Joanne and thanks to the maintenance community. I'm a relatively new member of the maintenance community. I only joined up about a month ago, but there's like some fantastic resources in there and some really good people too, right? I think that's kind of what makes the maintenance community what it is. So I'm looking forward to getting more involved.
Awesome. Well, thank you, Rafe. Have a great rest of your day. And then everyone else, I'll see you in Slack.
All right. Thanks, everyone. Bye.